Ever stop to think about something as simple as seeing an apple? It's not just about your eyes. It's actually this incredible journey that starts with a single ray of light. So in this explainer, we're going to follow that ray, from its source to the apple and all the way to the back of your eye. Let's get into it.
So let's kick things off with the most basic question of all. What actually makes things visible? Now your first thought is probably, well, my eyes, duh. But that's only half the story, right? Because if you're in a pitch black room, your eyes are pretty much useless. The real hero of the story, the secret ingredient, is light. But how does it all work?
You know, it really boils down to two kinds of objects in the universe. First up, you've got the light makers, what we call luminous objects. Think of the sun, a light bulb, a flame. They create their own light. And then there's pretty much everything else. Your desk, a book, even the moon. These are non-luminous. We can only see them because they act like giant mirrors, catching light from a source and bouncing it right into our eyes.
All right, so our little ray of light has left its source and it's zipping through the world. Its first big interaction is when it smacks into one of those non-luminous objects. So what happens next? Well, it bounces.
And that bounce, it's got a scientific name, reflection. It's literally just light hitting a surface and bouncing off. But don't let that simplicity fool you. This is happening trillions of times every single second on every surface all around you. Without it, you wouldn't be able to see a single thing that doesn't glow on its own.
Okay, so here's a question for you. If a mirror and a brick wall both reflect light, how come you can only see your face in one of them? This slide lays it out perfectly. A mirror has a super smooth surface, so all the light rays bounce off in this neat, orderly way. That's called regular reflection, and it gives you a nice clear image. But a wall, even if it looks smooth, is actually really rough on a microscopic level. It scatters the light in a million different directions. That's diffused reflection. You see the light from the wall for sure, but there's no coherent image.
And you know what's amazing? Underneath all this complexity, there's one beautifully simple rule that every single light ray follows. It doesn't matter if it's a perfect mirror or a bumpy wall, it always obeys the law of reflection. The angle it comes in at is the exact same angle it goes out at. As you can see right here, the angle of incidence equals the angle of reflection. Simple, predictable, and just perfect.
But our light ray's journey isn't all about bouncing around. Sometimes it has to travel through things, like moving from the air into water or through a piece of glass. And when it crosses these borders into new worlds, something really fascinating starts to happen.
We have all seen this classic illusion, right? You take a totally straight pencil, stick it in a glass of water, and suddenly it looks like it's broken right at the surface. Obviously, the pencil itself isn't bent. So, what is going on here? The answer to that little magic trick is a phenomenon called refraction. You see, as light travels from the air into something denser, like water, it actually slows down a bit. And that sudden change in speed forces the light ray to bend. So what you're seeing isn't a bent pencil. You're seeing the light from the pencil taking a bent path to get to your eye. Pretty cool, huh? But this bending of light has an even more beautiful consequence. Because it turns out that white light is kind of a trick. It's actually a mashup of all the colors of the rainbow, all traveling together as a team. And when that combined ray of light is forced to bend, something magical happens. It splits apart. This process is called dispersion.
And this slide shows exactly how it works. When white light enters a prism, or say a raindrop, each color inside it bends by a slightly different amount. Violet light bends the most and red light bends the least. This difference fans all the colors out, creating that beautiful spectrum we all know: violet, indigo, blue, green, yellow, orange, and red. This is literally how a rainbow forms in the sky.
Okay, so our light ray has bounced, it's bent, and maybe it even split into a whole rainbow of colors. But all of that is completely meaningless until it completes the final, most important part of its journey, entering your eye.
Seriously, just think of your eye as this incredibly sophisticated biological camera. The key players are the pupil, that's the little opening that lets the light in. You've got the lens, which does all the focusing. At the very back, you have the retina, which is basically the camera's sensor. And then there's the optic nerve, which is the cable that sends all the information to your brain.
So how do all these parts work together? Well, it's a super fast, four-step process. 1. Light streams into your pupil. 2. The lens focuses that light, creating a sharp but, get this, upside-down image on your retina. 3. The retina instantly converts that light pattern into electrical signals. And finally, 4. The optic nerve zaps those signals to your brain, which flips the image right side up and tells you what you're seeing. And this all happens way faster than you can blink. It's just incredible. This system is amazing, but sometimes the lens doesn't focus that light perfectly onto the retina, and this leads to some very common vision problems that I'm sure many of us are familiar with.
Let's just quickly break down the two most common issues, which this table lays out really nicely. So, if you have myopia, or short-sightedness, it just means your eye is focusing light a little bit in front of the retina, which makes things far away look blurry. A concave lens fixes that. Now, if you have hypermetropia or long-sightedness, the focus point is behind the retina, and that makes close-up things blurry. A convex lens corrects that. At the end of the day, glasses and contacts are just clever tools that give our natural lens a little help, making sure the light lands perfectly on the retina every single time.
And that's it. That is the incredible journey of a single ray of light, from a source all the way to your brain. But here's the part that really just blows my mind. Everything we've talked about, every single color you have ever seen, is just a tiny, tiny sliver of all the light that's actually out there. So the final question really is, what unseen worlds carried on rays of infrared or ultraviolet light are all around us right now, just waiting to be perceived?